Good morning, everybody, and welcome. Today's January 20th, and we're going to record our lecture 11 on thermodynamics. Just as an update, we've had a snowstorm overnight. I am here at the crack of dawn, bright and early in the morning. As you can see, we have snow outside of Haul Out Water Labs, and it's beautiful out there. All right, well then, time to get down to business. Today, we're going to talk about thermodynamics, which is a very useful topic and one which was very important for the Industrial Revolution. I don't need to start watch timer. So here I'm just getting everything set up to share my screen with you. Share screen. Share. There we go. All right. Now hopefully you can see that. Put our, okay, got it. Yep. Full screen. There we go. All right. So let's get down to this. And FYI, we also have exams today for the winter session. So it's possible, actually, it's almost inevitable that I will be putting this on pause and recording it in a couple of different segments because I do not have a full hour and 20 uninterrupted. But anyways, we make do, and it's part of everyday life. What is thermodynamics? Thermodynamics is the study of properties and relationships Is this continue writing behind this window? And properties of the system in equilibrium. Oops. EQIRIBRIM, which we will soon be writing as EQ. We'll have much more to say about equilibrium dynamics. So we're going to be doing the analysis of equilibrium properties, which is an important application to industries. We were mentioning the Bessemer process revolutionized the steel production. That actually happened right here in the USA. If you ever heard of Carnegie Steel, you might know something about that. You might know something about a guy called Josiah Willard Gibbs. He is from New Haven, Connecticut, and he was a very important person in working out thermodynamics. He was at Yale University for many years, and actually most of his life never even left Connecticut. So some very local history. Some of the things we're trying to predict is whether or not a reaction quote will go or not. And this is important to know because you might want to know if something's going to be happening or not. And we'll be taking a look at the Gibbs free energy and the alternative to the delta G, which is the Helmholtz free energy, which is a variation of that. There's quite a lot of applicability to a wide range of branches of science. You've probably learned about much of this in Gen Chem already. And this provides a macroscopic view of what atomic theory produces. So in other words, we have looked at the microscopic, very microscopic view when we did the quantum mechanics, and now we are moving into looking at larger systems from the top down. All right, so you know anything about thermodynamics from your Gen Chem or physics class, you have probably heard about work. Work and heat are the means by which energy is transferred between system and surroundings. So this has, of course, a lot to do about energy, which we talk about all the time, by which always in the news about climate change and so on. Transferred between system and surroundings. So oftentimes we do think about work and using pistons because this is how a lot of this was actually worked out. These days we may not use pistons quite as much as we used to, but there are a lot of things that do pertain to this. It's useful to understand a little something about how it works. The idea is you have some gas trapped in a piston, and then you run the piston. This is our piston here, and then we run the piston, or we look to see, like we either drive the piston or we look to see what happens with that piston. And this is how we're going to figure out what kind of work is happening. All right, so this app gets upset when it thinks I'm scribbling. So I don't know, it might be upset now. Oh, it's good. All right. So here is our piston setup. So I probably will not be drawing it quite so precisely every time, but I want to give you a sense of what piston looks like. Oops. And give you a sense of how you can draw pistons. Oh wait, I can do the undo. I learned about undo. Yeah, okay. Here we go. Piston in the cylinder. And of course, real cylinders are not clear. They're usually made out of metal because they're usually working in very hot systems, like in a car where things are burning. So making it out of clear plastic is not a wise idea. The system and surroundings. This, of course, is a somewhat contrived definition because, of course, can't really divide things out like that, but we can think about them that way. And that is the great thing. Okay, so Q is the heat energy transfer resulting from a change in temperature between system and surroundings. Why do we talk about all this stuff? Well, remember the gases expand when they heat, and they actually can push. Sometimes these things are not so obvious to us because we do not always experience these in everyday life the way people during the Industrial Revolution may have. A lot of these technologies, of course, are very polluting. All right, so heat is the energy transfer resulting from delta T between systems and surroundings. Now, we're going to need to keep very close attention to our signs. This is endothermic, which means heat is gained by the system. Whereas the exothermic takes a negative sign. I think of exo like exit. fluid is exiting the system. So when we're thinking about the system, we're also imagining that inside the cylinder, there is some gas. Okay, push our piston. Gas. Some kind of a gas in there that we're paying attention to for the system. Okay, there's a gas. This one. And then W stands for work. Work is about the exchange of energy. Between system and surroundings. As a result of unbalanced forces between the two. Now, we need to also pay attention to our work signs. We have a plus work. Energy of system increases. And this means work is done on the system by the surroundings. And conversely, negative would be energy of the system decreases. And this means work is done system does work on the surroundings. So then what we will visit is a number of situations in which these things are happening, and we'll learn how to calculate this. So this is called PV work, pressure volume work. PV work can be visualized as a piston which moves due to pressure or weight. And oftentimes in the depiction of the pistons, we don't actually show the forces, and it's kind of just left to be sort of nebulous, which I always found really confusing. So I actually like to draw out the weights on these systems because it made a lot more sense to me that way. So some of these I'm going to actually draw for you that way. Expansion. A lot of textbooks don't do that, and I don't really know why. It's just like this piston connected to nothing. All right. So here's a piston. Looks kind of like a beaker, but it's not. Now my cylinder has transformed into a piston. All right, here's our piston. And well, there's the actual piston. All right, and this has some depth, but this pen doesn't really like it very much. All right, and so there's gonna be a weight on top. So I'm gonna put a little box here. Okay, very heavy box, right? Some weight sitting on top of the piston. Now it's much more obvious what's happening, right? The piston is being pushed down and we have our gas inside. And so the gas is compressible, but only to a point, right? And so when you try to squeeze the gases, it will push back like a little spring. All right, so this again is gas, some gas here. Probably an ideal gas, I suppose, is very likely what we're gonna be thinking about. And here's our weight up here. And here's a movable piston, this disc thing right here. Right, and the piston can move up and down. So I'm just gonna do like this, right? The piston can move up and down. We could even write movable piston, and it will stay nice and stuck in the glass or in its thing here. We'll just do this to give it a little bit of depth. Yeah, it's just not like to. All right, so there we have our situation. There's a box sitting on top of a piston. We have a gas, we have a weight, which is representing external pressure, right? So in the situation of expansion, right? So how does this thing get expanded? Well, you heat the gas. So if you take the system and you heat it, okay, expansion of gas. Right, expand if the gas is getting heated. Now, one thing that I always found kind of confusing about these explanations is that heating the gas kind of seems like something going on externally, which it kind of does, but it sort of depends how you define your system and the work. So, and here's the weight. So very heavy, but and here's the old, okay, here's the piston. These are not beautifully round like they could be, but we'll pretend a bit. All right, there we go. Okay, there's our piston, and the old position of the piston is right here, right? That's where it used to be. And it has moved up. Right, it's gone from there to here. Delta H, change in height. This is the height initial, and this is the height final. And it is risen. So we should probably put a flame in here to remind us that, do we have a red color? All right, we'll use this one, marble. So what happens is we've started here and we have heated the gas. Okay, there's a hot flame under here. Heat the gas. Of course, we know from our, from our other discussions that that we really do not. Red is really not actually the hottest, but heat the gas is what's happening over this arrow. back to blue. All right. And so now the pressure final that we have from our gas. Oh, we need to put our gas in. All right. So the gas is now gonna be a lot less dense than it was before. So it's in a much larger volume. There it is. All right. So now we need to note that the pressure final equals the pressure external. But of course, the gas is warmer than the gas outside, which is also something we need to keep in mind. All right, so my 20 minutes is up and it's time for exams. So let me, piston moves up, the gas expands. The system does work. And by the system, we mean the gas down here on surroundings. In other words, it raised the box up because it pushed the piston up. That was not an intended thing. So my wrist. Piston moves up. The system does work on surroundings. W equals negative P external delta V. This negative sign right here is external pressure, aka the box. This little box sitting right up here. Here, we could even do like this. Put EXT on it to remind ourselves this is the external effects. All right, that is our external effects, and that is what has happened. All right, and let me just check the time. All right, I'm gonna need to pause this video for a second, but we shall be back soon. So I will pause the video.